Hello, everybody. Thanks once again to the organizing committee, Indian Nuclear Society and NBTIL for inviting me. I'm really glad to be here and see all of you. I was really amazed by the number of topics related to the SMRs during this conference. I thought there will be maybe my presentation and presentation of my colleagues from EDF and Westinghouse, but finally we hear something about SMRs in each presentation. So it's a bit wonderful to me. So I will try to be not really annoying regarding this topic and diversify a little bit the SMR subjects with some large-scale MPPs as well. But firstly, a brief introduction. You know, the engineer is a person who invents something, who tries to make processes working, who tries finally to avoid working by himself and enhancing these processes. So finally, an engineer is a lazy person because he wants something working at his place. I'm an engineer. So that's why, instead of brief introduction, we will see a short video. The sound is working? Yeah, you can stop the video meanwhile for a second. Yeah, I'm trying to break the rules and show the video in the beginning of the presentation instead of showing it in the end. Yeah, thanks.
In our modern world, there are places that need energy. Clean, safe, reliable. Just like the energy of an atom. In recent years, more and more attention has been paid to small modular nuclear reactor technologies. Aside from the vast experience in design, manufacturing, construction, and operation of large-scale NPPs, Rosatom boasts an impressive record of small reactor technology development for the icebreakers. More than 400 reactor years. Basing on this unique icebreaker experience, Rosatom has implemented the world's first and only floating nuclear power plant, Academic Lomonosov. Set sail across the 7 seas. Its destination is the town Pevek in Chukotka. And now, Rosatom is prepared to offer an optimized floating nuclear power plant to the global market, which is designed to address most peculiar customer demands and site specifics. FNPP can supply power, heat, and desalinated water to coastal areas, offshore installations, islands, and archipelagos. FNPP is equipped with 2 SMRs of Rhythm Series. Rosatom Rhythm Series is the latest development in Rosatom's 3+ generation SMR line, which has incorporated all the best features from its predecessors. Rhythm Series is an integral pressurized water reactor. Safety of Rhythm Series is ensured by Defense in-depth principle. Aside from the floating offshore solution, Rosatom is developing an onshore small NPP based on Rhythm Series SMR. Active and passive safety systems based on redundancy, diversity, and independence principles are implemented in design of Rhythm 200. In the onshore option, SMR NPP reactor building ensures SMR units protection from external hazards, such as impacts of windstorms, tornadoes, sandstorms, aircraft crash, wind loads, and impacts of extreme temperatures. Thus, the reactor building acts as an additional safety barrier. Modularity is what makes SMR-based energy solutions so attractive for remote areas. It allows to adjust plant capacity to actual power demand by adding new modules. All modules are prefabricated, which significantly reduces the cost and construction period. Rosatom supports its customers throughout the civil nuclear program, from the very introduction of a nuclear option to decommissioning of the last nuclear facility. Smaller solutions for a bigger future.
Yeah, thank you so much. It's nice marketing videos. Thank you. I'm finished. I'm done. So, being serious, we have seen and observed in the numerous presentations the interest to the SMRs. So the reasons have been discussed largely in the previous presentations, so I will not stay on it for a long time. But probably just 2 points that I would like to highlight. It's lower absolute capital costs compared to the large-scale NPPs, which reduces as well the risk. So even if you overpass the delay of construction, the financial risks are lower. And as well, due to the modular fabrication and prefabricated pieces, the construction itself is eased. For the remote areas, it's a really interesting offer. For example, as you have seen, this academic Lomonosov floating NPP, it has been used to replace the old coal plants in the city of Pevek to provide the district heat and provide the electricity to the nearby mines. As well, you know that in this region we have a very old small reactor. 3 of them are operating now, 12 megawatts. And they will be replaced as well by this power supplied by these floating units. You know that we have as well 4 more floating units that will provide energy to the gold and copper mine. And finally, we have the design of the land-based SMR in the Yakutia region that will provide as well the energy for the mining complexes. It's a remote area, completely isolated, no grids, such as developed in India, and the interest of this object is that it's difficult to construct. It's far away from anything, from the infrastructure, so everything will be brought in place by modules. The status of this project is we have obtained the siting license in April. Now we have submitted the package of documentation for the state expertise organism that will check the design and the costs. And I guess in February, the dossier will be submitted to the safety authority to get the construction license. And we expect the first concrete in the summer next year. So let's go through the taxonomy of nuclear reactors in Russia. And I will explain why it's interesting. So, you know already VVR series reactors. I won't explain it to my colleagues from NPCIL, you know it very well. So we have discussed yesterday during the panel session about the optimization of costs and standardization. I had some questions about how it will be standardized, how we will reduce the cost, how we will reduce the construction time of these units. So finally, you know that we have VVR toy, which is under construction now and shall be in operation in 2025, which in the basis contains these optimized solutions. Standardized and 3D modeling is integrated within this reactor and the management system. It has the same, almost the same electrical output as VVR 1200. However, that one is also, I would say, optimized and standardized solution. So that is that we are proposing for the new site for NPCIL. Next branch of reactors are the sodium-cooled reactors. So the history starts in 1958, quite old series of reactors. So the last one, the project which will start soon, is fast neutron 1200. Why we have chosen such capacity is to match with VVR 1200 and VVR toy to optimize the turbine generator island and use the same capacity. So the third one, it's a bit sad story about this RBMK type reactors. You know, it's a dead-end story. The idea was good. You use natural uranium, you have a large capacity, but finally no compromise on the safety, so it's a dead story. And the SMRs as well. It's to say that they have been developed in Russia as a separate kind of reactors. They were used firstly on as icebreakers for this series. So first one loop type, second one loop type, third one loop type as well. And then we have passed to the integral type of reactor, accumulating the experience of the previous ones. I will explain why in details on the next slides. So typically that one is installed on the floating unit and provides energy and the heat district to the city of Pevek. Let's jump inside of this reactor. So it's an integral type. The core is quite compact. It's about 1.7 meters height. 199 fuel assemblies for the land-based version. It will be 241 for the floating units. It allows, together with a high enrichment, to get the reloadings once per 6-7 years, and for the floating unit, more than 8 years. Quick power change rate. It's designed for the floating units. It means that you need to drop the power quite quickly, because it's like a car. 4 main circulation pumps situated here. Steam generators over there. And finally, this is an integral type of reactor. It provides steam, so you can place it everywhere you want. So if you want to provide the steam for industrial purposes, it can be suitable for. Control rod and safety rod, so to control the reactor and to shut down, are based on those used on KLT-40S, as well as the main circulation pumps. So it's a direct successor of the previous generation. So we have all the feedback, all experience. It supports base load and the load following modes, which is quite interesting to compensate renewable energy sources. And the daily following mode provides operation up to down to 20%. Typically, the reactor itself can go down to 10%, but due to some turbine reasons, it's not wishable. So, about the safety barriers, just to see how it matches. So, it's not a uranium oxide, it's uranium oxide dispersed in the silicon matrix. Corrosion-resistant fuel cladding, because it needs to support high burnout and as well a long fuel reload cycles. The core is reloaded integrally. It means that you remove everything and you put a new core. Reactor coolant system with auxiliary systems. So the integral advantage of the integral type of reactors that you avoid large break locus. They are not possible in that one. Only small breaks of pressurized tubings, etc. So the biological shield, metal water protection. You have water inside. Why? Because the reactor itself is small, and you need to have a good biological protection. But it adds some as well safety functions. In the case of core melting, you can keep it inside. So it can be cooled down, even in the loss of energy. So, and the full system with the containment looks like that for the land-based version. And on the video you have seen the square containment is for the floating units. Typically, it depends upon the optimization in the accidental scenario. So, the safety concept is the following. It combines the passive and active systems. There is no boring regulation. If we shut down the pumps, the heat removal may be done naturally in a safe manner. So the height of the reactor itself is about 8 meters plus 1.5 meters for the top. It can be easily transportable by the railroads, and regular roads, because it's compacted. The maximum dimension in diameter it's 4.6 meters due to these main circulation pumps, and the length of the RPV itself is about 8 meters. So, what about the cost? Probably it's the most interesting subject that we have discussed during the last days. So no, I will not show you the cost. But this is the road how we can achieve it. Firstly, we have the most important stakeholders, which are the government, who wants a safe, reliable, and economically competitive solution. We have the suppliers, which were presenting their solutions. They expect a firm order and understandable policy and as well a vision of the government. They want something from vendors and they want something from government. And at least we have vendors that expect certainty and a clear request from the government to go together with suppliers. Nowadays, we have 3 non-deformable spheres that are moving but cannot interact. So what is the solution to get this magical beast, which is economically viable and interesting SMR? But it's here. It's hidden over there. We need to make interacting all these stakeholders. The other ones are hidden behind, for sure. But these cost-effective SMRs are hidden in this area. So I guess it's the same message that has been passed during all this conference. And I guess we all agree about it. Let's do it that way. And finally, you know, we have a good example from the past. Do you remember the automobile era? How it has started? Only with several samples. Not really understandable why would we use it. We have horses, we can use them. Why will we drive such strange thing? It will cost a lot. To construct it, we do not even know how much time. It's a piece by piece samples. Then the projects have appeared. Still the future has been unclear. It was too expensive. How to advance on it? Finally, we have almost all now automobiles. The future is here. So we need to make a step forward, and the government shall take its responsibilities to get these costs dropped for the SMRs. I'm done. Thank you.